So in this session on signals and systems, we are going to study digital filters. So let us start. Let us start by answering the question, what is a filter? Now, the answers that we are giving will be applicable to both the analog filters as well as digital filters. Although in this particular session, we will be concentrating on digital filters, but some of the concepts are common. So I'll be pointing that out from time to time. Okay, so what is a filter? Now, if you take any signal, you will generally find that it contains number of frequency components, but some of them are desired frequency components and some are the undesired ones. So filter is a circuit which will allow the desired frequency components to go through and reject the undesired ones. Okay, so let me repeat that. Filter is a circuit which allows the desired frequency components to go through and stops the undesired components. Okay, so the question now is, which components you call as desired and which you call as the undesired frequency components? So as I said, let me repeat that, which are the desired and which are the undesired frequency components. So this depends on application. For example, if you are trying to build an audio amplifier, the desired frequency components lie in the frequency range 20 Hz to 20 kHz. Outside this range, noise is present everywhere. So you would like to remove the noise. So in that case, noise is the undesired one and the frequency range from 20 Hz to 20 kHz is the desired one. So let me repeat that. For audio amplifier, desired frequency components range from 20 Hz to 20 kHz, but noise has components over much wider range. So the noise outside the desired range needs to be rejected and hence you require a filter. Let's look at another application. In a radio broadcast, the receiver antenna receives signals from all stations, but you want to tune to a specific station. Hence, a filter is required to reject stations with nearby frequencies. After all, you are going to listen to one station at a time, so you would like to reject the other ones. So these couple of examples, there are many more examples, but these couple of examples will do for the time being, and they tell you what are the desired components and what are the undesired ones for a typical application. All right. Now, before we can study how to design a given filter, it is important to study certain basic concepts which will be applicable for the design of digital filters. So let us study some of these concepts. Now, if you take any signal, it has a time domain description and it also has a frequency domain description. And there is always a link between the time domain description and the frequency domain description. And this link can be expressed in various ways. But we are going to study one particular way which will be useful for the study of digital filters. So let us start by writing the equation for a signal, which in this case we have chosen a simple sine wave. And this is of course a continuous time signal, but whatever discussion we make will be applicable to both continuous time as well as discrete time signals. So let us look at both the equations. Xt is a sine omega t. So the discrete time equation will be xn will be a sine of omega n. Now what we do, we want to find the slope of these two signals. So we differentiate it with respect to the independent variable. So dxt by dt, as you can see, is a omega cos omega t. Similarly, you can find the equation for the slope of the discrete time signal. That is also similar, dxn by dn. That will be a omega cos of omega n. So clearly this slope depends on the time. At different times the slope will be different because of this cosine function. However, the maximum slope will be equal to a into omega. That is the maximum slope. And this equation tells us that larger the value of the frequency, higher is the slope with which the signal changes. So the rate of change of signal in the time domain corresponds to high frequencies in the frequency domain. That is what this equation for slope tells us. So this is one important concept. Signal having higher frequencies will change more rapidly. Or conversely, you can say a signal which is given to you and you observe that it is changing more rapidly, then you can conclude that it will have higher frequency content. So let me show you a specific example of this. Look at the two waveforms. This is a pure sine wave, so clearly this is only one frequency component and the time period is 0.01 second. That means the frequency of this sine wave is 100 hertz. And you can see that the slope of course keeps on changing, but to get some idea of the rate at which it is changing, you can see that it jumps from 0 to 1 in a time which is equal to 0.0025 seconds. Now let us look at the other waveform, which is similar to a square wave, but it has some ringing present here. But the point is, this is a waveform obtained by adding number of harmonics to this fundamental. So if you look at the fundamental frequency of this second waveform, that is still 100 hertz. But because it has a number of harmonics present, high frequency components present, so because of that you find that the slope is high. And you can see that it changes from 0 to 1 in much shorter time compared to the pure sine wave. So this demonstrates to you that a signal having higher frequency components will be changing more rapidly. Okay. So now let us consider an example. See, we have said that a filter is a circuit which will allow the desired ones to go through and reject the undesired ones. So there are a number of filters possible. You may allow low frequencies to go through and reject the high frequencies. That will be a low pass filter. But you may allow the high frequencies to go through and stop the low frequencies. That will be a high pass filter, and so on. But right now we just want to quickly study how we can implement a low pass filter. Okay. So consider a low frequency signal with high frequency noise. Okay. So we have a desired signal which is a low frequency signal, but it has added to it a high frequency noise which is the undesired one. So since this we want to reject, we want to allow the low frequencies to go through and reject the high frequencies. Therefore, the filter that we will require will be a low pass filter. Okay. So as I said, we need a low pass filter to remove the high frequency noise. Now how to do this? This can be done by calculating the running average, because of the high frequency noise occurs. In general, it may not occur everywhere. Okay, it could, but usually the design of the systems is such that the signal amplitude is generally kept large with respect to signal. So when the high frequency noise occurs somewhere, suddenly there will be rapid changes, and these rapid changes we want to remove. So that can be done by calculating the running average. So let me demonstrate this to you, how the running average will reduce the rapid changes in data, and therefore the operation of calculation of running average will act like a low pass filter. Whether you implement it as a circuit or you write a program for doing this, the action will be that of a low pass filter. So let me demonstrate to you through some waveforms. Let's say this is my desired signal. In this case, I have considered a very simple signal which is remaining constant throughout, so it's a DC signal. But let's say there is some high frequency noise burst which occurs. So right from the sample number 0 up to sample number 19, first 20 samples nothing is happening. But here you suddenly find that you get some additional samples which are the noise samples. And you can see the slope of this is much higher than the slope of the desired signal. In fact, we have considered a very simple case. So the desired signal, the slope is 0, whereas the noise clearly has a larger slope. So when this noise gets added to the signal plus noise will look like this. So for most of the part it is same as signal, but where the noise occurs, this suddenly changes. And by computing the running average, we would like to reduce the effect of this sudden change. In other words, we would like to reduce the high frequency noise. Now, why would that happen when you calculate the running average? So understand this. Let us take the first 20 samples. So 0 to 19, sample number 0 to sample number 19. There are 20 samples total. So that is corresponding to signal itself. You will get the exact value. That will be 10 itself. But as you take the next sample, say from sample number 1 to sample number 20, then you find there is an increase here. So when you calculate the average, this will increase the value of the average slightly, but it will not change too much because most of the samples are having the desired value and only one sample. When you take the next one, these two samples will cause a problem. So the output may increase slightly more. Nevertheless, you see that in this case, the noise increases to a maximum value of 4, whereas our original signal has a value of 10. So when you calculate the running average, the effect of the noise on the running average in general will be less. And if you do this calculation, the kind of output that you will get will be like this. Most of the time it is 10, but somewhere in a short period of time, you will get slight increase in this. So if you compare this with the original signal, what you have done is by calculating the running average, basically you have removed the noise or at least reduced the noise. So it will work like a low pass filter. All right. So let us try to study this mathematically now and write down the equation for the calculation of the average. So Yn. So Yn is what? Is the average of n samples. In our example, we had considered this capital N as 20, but in general, I am saying n number of samples over which you calculate the average. Now, Xn is the current input value. Xn minus is the input value one sample time earlier. So this has to be stored. You'll require memory. Filters will always require memory. For example, just to give you an idea from analog filters, using pure resistors, you can never build a filter. You will require either a capacitor or inductor, which are basically memory elements. So from analogy to analog filters, you can say that digital filters will also require memory in order to implement a filter. All right. So Xn minus 1 is the previous value. Xn minus 2 is 2 samples earlier and so on. So all these samples are stored and this is the current value. So obviously to calculate the average, you add up all this and divide by n. So when you do that, you can write each sample value multiplied by a coefficient which is constant and which is equal to 1 by n. So this is 1 by n, this is also 1 by n and so on. So this is your input output equation for a filter. Although in this particular case, the coefficient that we have got is same everywhere. This was a specific case of implementing a low pass filter. But in general, you will find you will be able to build a better filter by using a weighted average. We'll see later on how the values of the weighted average are calculated. But right now, let me just give you a more general equation for the filter for the output in terms of the input. So when you write the weighted average, the more general equation is that all coefficients are different. So you can get B0 into Xn plus B1 into X minus 1 plus B2 into X minus 2 and so on. And the kind of response that you get from the low pass filter and the nature of the filter itself will depend on the values of B0, B1, B2, etc. This is quite a general equation for a filter, and you can build a low pass filter or a band pass filter or a high pass filter and so on. Of course, the values for various coefficients will be different for different kinds of filters. So later on we'll study how to obtain these B0, B1, B2 for implementing various types of filters, and also how understand one thing, that the number of previous samples that we are using, the larger the number of samples we use, better will be the quality of the filter. This is like saying if you want a analog to the analog filter, there remember, if you have a number of filters cascaded, more number of filters you cascade, sharper is the response as you go from pass band to the stop band. So similarly here also, more and more sample values that you store and use, you will find your filter will have a better response. Anyway, the point is, if you can calculate B0, B1, B2, etc., all the coefficients, then you have essentially designed the filter. So question is how to get B0, B1, B2, etc. And the answer to that is, we'll be able to show mathematically that the sequence of coefficients also corresponds to the impulse response of the filter. So this is one particular property that we will just now show, and later on we'll see what is the significance of that. So let us study the impulse response of the non-recursive filter. Now, although you can have large number of previous stored values, but here I have taken only the current value and two previous values in order to keep the equation simple. But this can be extended to larger number of stored values also. Now, so this is our basic equation for equation with three equation for the filter with three coefficients. And what do we want to show? We want to show that the sequence of coefficients also equals the impulse response. And what is an impulse? If xn is the input, so impulse response means what? When input is the impulse, what is the output? That is the impulse response. So if we replace xn by delta n, so this will be delta n, this will be delta n minus 1, this will be delta n minus 2, and then calculate yn for various values of n, then we'll be able to show that the sequence of coefficients also equals the impulse response. So let us do that. So let xn first of all equal to the unit impulse at the input. So let us rewrite this equation by using delta n in place of xn. So we'll get yn equal to b0 delta n plus b1 delta n minus 1 plus b2 delta n minus 2. This is the equation for the output if the input is a unit impulse. Okay. Now let us calculate the output values for various values of n. So first suppose n is equal to 0, the sample number 0, y 0. So this is equal to b0 delta n is equal to 0 plus b1 into delta minus 1 plus b2 into delta minus 2. Now if you remember your digital unit impulse, we are talking about a digital filter here. So if you remember the property of the digital unit impulse, you will find that it has a unit value at n equal to 0, and for all the values of n it is 0. That means this will be 0 and this will be 0. So in that case y0 and delta 0 is 1. So this will tell you that y0 is equal to b0 itself. So first value of the output corresponds to the first value of the coefficient when input is a unit impulse. Alright. So that was the calculation we did for n equal to 0. Let us now do for n equal to 1. So y1 will be b0 delta 1, okay, n equal to 1, plus b1 delta n equal to 1, so this is delta 0, plus b2 delta minus 1. Again remember that delta 0 is 1, delta 1 is 0, and delta minus 1 is also 0. So in this case y1 will be equal to b1. Finally, similarly you are able to show that y2 will be equal to b2. And once n exceeds 2, it's easy to show that yn will be equal to 0. You can try it out yourself. It's easy to show that because you will not get the term delta 0 at all. So you'll get yn equal to 0. So what have we shown? We have shown that yn is equal to b0, b1, b2 when the input is a unit impulse. In other words, the impulse response is also equal to b0, b1, b2. Okay. Now, as you can see, the duration, this is the impulse response and the duration is finite, clearly. So since the duration of the impulse response is finite, this kind of filter is also called as finite impulse response filter or an FIR filter. Okay. But what is the significance of the fact that the impulse response corresponds to the sequence of coefficients themselves? Okay. So the point is that impulse response forms a Fourier pair with the transfer function. And usually the filter specifications are given in terms of transfer function. So if the filter specs are given in terms of transfer function, we take the Fourier inverse, obtain the Hn. When we obtain the Hn, we automatically obtain B0, B1 and B2. That is the significance of this particular property. So therefore, let us revise our concepts of the transfer function and also show that transfer function forms a Fourier pair with the impulse response. That is your Hn. Okay. So what is the transfer function? So as we said, the filters are defined by specifying the transfer function. Later on we'll see how this specification is done. But transfer function itself is defined as the ratio of the output to the input where xn is e raised to j omega n. You will remember this from your study of sinusoidal steady state. Of course, in some of the previous courses, you must have done that for analog signals. So this would have been e raised to j omega t. But we are now talking about the discrete signals. Therefore, xn is e raised to j omega n. So what are we saying? We are saying that transfer function is the ratio of the output to input when xn is e raised to j omega n. Okay. Now what we want to do? Let us do that. Now for any given xn, yn is given by the convolution sum. Remember that yn is obtained by convolving the impulse response with the input. So this is our general equation. But in this case, xn is equal to e raised to j omega n. So we substitute for x here and this n is of course replaced by n minus k. So this now becomes e raised to j omega n minus k. You expand this, so this is hk into e raised to j omega n into e raised to minus j omega k. Now if you look at the summation carefully, the changing variable is k and not n. So therefore this term e raised to j omega n you can take outside the summation term and write it like this: yn is equal to e raised to j omega n, k equal to minus infinity to plus infinity hk into e raised to minus j omega k. But what is this? This is the definition of the discrete time Fourier transform for the signal hk. But hk is what? It is the impulse response. In other words, this particular quantity you can write as the Fourier transform of hk and write it as h of e raised to j omega. So now you can show that the Fourier transform of the impulse response is also equal to the transfer function, because it's easy to see now. H e raised to j omega is yn upon e raised to j omega n, and that is your definition of transfer function. Remember, this yn by xn, where xn is e raised to j omega n. So this is yn divided by e raised to j omega n. So what have we shown? We have shown that the transfer function is the Fourier transform of the impulse response Hn. And it is usually the transfer function which is specified in filter specifications. So if you take the inverse Fourier, you will get the impulse response. Once you get the impulse response, you know that the impulse response corresponds to coefficients. So you get the coefficients and you have designed the filter. All right. So, but before looking at the design itself, we'll take a quick look at how the filtering action is done, just to revise our concepts of filtering vis-a-vis the transfer function. So let's say XA is given by sum of three frequency components: omega 1, omega 2, omega 3. This is just one example. In general, you can have a range for low frequency components, a range for mid frequency components, and a range for high frequency components. But to keep things simple, right now, I have considered only one frequency in each of these. Okay. Now, if you look at the transfer function, h of e raised to j omega, this is a complex function of frequency. So it will have a gain, magnitude, and the phase angle. So let's say that its magnitude, that is magnitude of this complex function, is h1, and the phase angle is phi 1 at omega equal to omega 1. Remember, this is a function of frequency. So for these frequencies, both h and phi are going to be different. So let us say h1 and phi1 are the magnitude and phase at omega 1. Then let us say h2 and phi 2 at omega 2. Then h3 and phi 3 at omega 3. Alright. So now it's somewhat easy to understand the filtering action by calculating the output. So when you calculate the output, what happens? Each input amplitude gets multiplied by the corresponding gain. So for omega 1 it is h1. So A gets multiplied by h1, and to omega 1n you add phi 1, that is the phase angle. So first term becomes like this, second term is this, and this is the third term. So now depending on how you have designed your transfer function, you can build a filter. For example, if h2 and h3 is equal to 0, suppose h2 is 0, h3 is 0, so no matter what b and c etc. are, these two terms will vanish from the output. So you will get only low frequency. I am assuming that omega 1 is the lowest frequency, the next frequency is omega 2, and the highest frequency is omega 3. So omega 3 is greater than omega 2 and omega 2 is greater than omega 1. So if we say that h2 is equal to 0 and h3 is equal to 0, then these two high frequency components are eliminated. Only this is kept and you get a low pass filter. On the other hand, if h1 and h2 are 0, then only the highest frequency will go through, and you can call that as high pass filter. But if h1 and h3 are 0, okay, this is 0 and this is 0, then it is the middle range of frequencies. In this case there is only one frequency. In general you will have middle range, so that this will be passed. So that is called as a band pass filter. If h2 is equal to 0, band reject. So whatever frequencies that are lying in the mid range, they are rejected, you get a band reject filter. So this simple calculation gives you some idea as to what is how the filter functions and what is the significance of the transfer function in terms of its magnitude and phase angle when you are trying to design the various filters. Alright. Now this is as far as this rejecting the undesired ones. But in the desired frequency band, what is the characteristics? Transfer function characteristics for the designed band. Understand that we had said omega 1 is the lowest, then omega 2 and omega 3. But in general, you will have a low frequency band, you will have a mid frequency band, and you will have a high frequency band. And when you are designing a filter, you are allowing a low frequency band to go through, or mid frequency band to go through, or high frequency band to go through. So we now want to understand what should be the transfer function characteristics for the desired band. So clearly this characteristic should be such that the signal should not be distorted. So suppose this is my desired band, okay, which contains frequencies from some frequency which we call as minimum omega min to omega max. And understand, I am talking not about high or low or mid band. This could be any band. So this may be low frequency band, this may be high frequency band, or it may be mid frequency band. What we are trying to say is that whatever is the desired band, for this desired band, what should be the transfer function? That is what we want to find out. So clearly now what the filter does is it multiplies each frequency by the corresponding amplitude. And if you don't want the waveform to change shape, that is, if you don't want any distortion, which of course you don't want in the desired band, then the gain must be constant for all frequencies in the band of interest. So this should be constant. A min, A max, etc. are the amplitudes of the various frequency components. But as I said, omega min is the minimum frequency, omega max is the maximum frequency, and what we want is that each frequency component should be multiplied by the same gain. That is, A min is multiplied by AH, A max is also multiplied by H, and all intermediate frequencies which are lying in this band also should be multiplied by the same gain, which is the magnitude of the transfer function. Also, delay should be same. Understand, delay and phase are related to one another, but in order to avoid distortion, the delay must be constant over the entire frequency range. So in the case of a discrete signal, delay of course is in terms of number of samples. So we have said that ND is the number of samples by which the signal gets delayed as it passes through the filter. So what we are saying is that for the band of interest, not only the gain be constant, which is the magnitude of the transfer function, but the delay provided by the filter also should be constant. So H is constant over the range omega min to omega max. ND is constant over the range omega min to omega max. But this is related to phase. So let's see if you now this equation I have written can correspond to any of these terms. So I have written in general some x amplitude multiplied by h cos of, now if you expand this, omega n minus omega nd. So it is this minus omega nd which corresponds to the phase angle phi. So what this tells us is that the transfer function of the filter should be such that over the pass band of interest, its magnitude should be independent of frequency and its delay should be independent of frequency. In other words, its phase angle should be linearly related to the frequency. Understand this clearly. It is the delay which has to be constant and not the phase angle, unless it is zero. If phase angle is zero, which is not possible for all frequencies in a practical filter, theoretically you may say that if phi is equal to 0 for all frequencies, it doesn't matter. But in general, delay must be constant and therefore the phase will be linearly related to omega. Alright, so in this session we have defined what a filter is, and in general we have seen what is the relationship between the coefficients of the filter and the impulse response, that is same. And then we have studied the basics of the transfer function, and we have said what should be the nature of the transfer function so that there is no distortion of the signal in the band of interest. All this we have studied. In our next session, what we are going to do is to see if the transfer function is specified, how to find the impulse response. Basically you do that by finding the inverse Fourier transform, but that is reserved for the next session. As far as this session is concerned, that's all.